Okay, I think we're good.
Okay, great. Welcome everybody to the 4th session of the AABI Symposium this year. So today we have one very exciting lecture and also 2 exciting contributory talk. So the first lecture will come from Fredrik Lindsten, who is a associate professor at Linköping University. So he's interested in machine learning and statistics, and he is very well known for his contribution to sequential Monte Carlo and also other things related to approximate inference. So today, Fredrik will tell us about sequential Monte Carlo for approximate Bayesian inference.
Okay, thank you very much for the nice introduction and for giving me the opportunity to join this symposium on AABI and talk about SMC for approximate Bayesian inference. Okay, see if I can switch slides. There we go. I decided to structure this talk into 2 parts, where the first part will be something of an introduction to SMC. This is, I could say, inspired by a recent Foundations and Trends paper that I wrote together with Christian Nesset and Thomas Hyun. So for all of you who are experts in SMC, this will probably be mostly familiar to you, but I hope that it can provide some additional sort of insights or maybe a different perspective of SMC. And then in the second part, I will talk about a particular application of SMC towards inference and probabilistic graphical models, and we'll see how we can combine SMC with other deterministic approximation methods. And this is based on a paper from NeurIPS a couple of years ago, together with Joni Helske and Matti Vihola. Okay, but let's dive into the elements of sequential Monte Carlo then. And the problem that we will be concerned with here, I think, is familiar to most of this audience. So we will try to approximate some target distribution, some probability distribution of interest that I denote by pi of x. And we will assume that this distribution can be evaluated up to normalization. So we can evaluate this unnormalized target gamma of x, whereas the normalizing constant z is assumed to be intractable. And the typical or most common example of this is, of course, in Bayesian inference, where pi of x, our target, is the posterior distribution over some parameter or latent variable x, conditionally on some data. The gamma will then be the joint over x and y, and the normalizing constant z will be the marginal likelihood of y. Okay, so a basic Monte Carlo algorithm that can be used for addressing this problem is importance sampling. And in importance sampling, instead of sampling directly from pi, which we assume is intractable, we generate samples xi by sampling independently from some proposal distribution q of x. And then to account for the discrepancies between pi and q, we associate these samples with some importance weights. And since we now assume that we can't evaluate the normalizing constant for pi, we first compute these weights by taking the unnormalized target gamma divided by q, and we then normalize the weights to sum to 1. And this will then give us a collection of weighted samples that can be used to construct an empirical or weighted empirical measure like this, pi hat, which is then a point mass distribution with point masses given by the samples xi, and each point mass has an associated probability of wi, the importance weight. And we can then view this empirical measure as an approximation of the target distribution pi hat. A nice byproduct of this importance sampling algorithm is that it will also give us an unbiased estimate of the normalizing constant z, simply as the average of these unnormalized importance weights. And this is nice because in many applications, we're actually interested in the normalizing constant as well, in particular, or for instance, in Bayesian setting when this corresponds to the marginal likelihood. Okay, so while simple and elegant, there is a basic or fundamental issue with importance sampling, or the standard importance sampling method, in that it scales poorly with dimension. So in most challenging high dimensional problems, we need to do something more to get the practical algorithm. And to pave the way for SMC, I will now assume that this variable of interest, x, can be split into n different components, x1 up to xn, where each such component, so xt, lives in some space that I call curly xt here. And in particular, or these spaces xt can be quite arbitrary. So the different components need not be scalars, but they can be some vectors of parameters, for instance. But we have this this structure on the variable that we want to sample. Okay, and based on this, we'll then introduce a sequence of target distributions, pi t. And this sequence of target distributions is defined on a sequence of spaces of increasing dimension. And this is kind of the basic property that we need for being able to apply SMC. And what I mean by this is that pi t, the target distribution at iteration t, you could say, that's a distribution over the first t components, x1 up to xt, which then lives in this product space of the curly x1 up to curly xt. So the most typical example of this, and also where most work on SMC has been done, is of course for inference in dynamical systems or state space models, in which case the index variable t here corresponds to some time index, and the target distribution will be the distribution of some system state conditionally on all the measurements or all the data observed up to time t. But as we'll see, the SMC framework is in fact much more general than this, and it can be applied to other settings that are not, or that don't correspond to dynamical systems, or that don't have a natural sequential order. Okay, so in this setting, sequential Monte Carlo is simply an iterative application of self-normalized importance sampling for tracking this sequence of target distributions, starting with pi 1, moving to pi 2, etc., all the way up to pi n. An interesting thing to note here is that in a lot of applications, and not least when looking at applications in machine learning, our interest is only in the final target distribution pi n. And all of the intermediate targets can then be thought of as just a vehicle for arriving or obtaining this final target that we're actually interested in. And this means that all the intermediate unnormalized target densities, these gamma t's for t going from 1 up to n-1, can be viewed as design choices in the SMC algorithm. And this is something that I will get back to later on. But first, just to show you some examples of where this is indeed the case, that we're can use SMC for tracking a sequence of distributions when we want to arrive at some final pi n. I will show you a few such examples. And one example is in probabilistic programming inference. So probabilistic programming we can view as a way of overloading or designing a programming language such that some standard programmatic operations have probabilistic meanings. And this is a nice way of providing like ergonomic support for implementing and reasoning about probabilistic models. So in such a program, we're interested in doing posterior inference over the program itself. So we can then view this index variable t, or the time variable, as a sequence of, or indexing a sequence of checkpoints in the program. And x1 up to t will then be the memory state of running the program up to checkpoint t. And in such a program, what we're often interested in is to do some automated inference, meaning computing the posterior distribution over the program state after a complete execution of the program, conditionally on the observed data. So that's one example where SMC can be used, and actually a lot of probabilistic programming languages do have support for SMC, and it lends itself quite natural to using SMC-based inference. Another application or example where it's perhaps not as obvious that we can use SMC is for inference in probabilistic graphical models. So if we consider some factor graph over a collection of variables x1 up to xn with a factor set f, then the joint distribution over these variables will be given by a product over some factors fj, where each factor here depends on some subset of the variables according to the graphical model. For such a model, we can introduce a sequence of target distributions through a so-called sequential graph decomposition. And what I mean by that is simply that we order the variables in some way, and we then define these unnormalized intermediate targets by simply taking the product of all the factors depending only on the variables x1 up to t. So gamma t will be the product of all factors over the factor set where the factors depend only on the first t variables in this sequence. And we can then track this sequence of target distributions using SMC, and at the end we will then obtain a target distribution which corresponds to the full distribution over the graph by construction, where we then include all the factors. And as a final example, I can mention tempering, where we can gradually move from some simple distribution, which I denote by this pi tilde 1 here, to some complicated target distribution pi tilde n. And this could, for instance, be if we have an IID, conditionally IID data, then we have a prior over some parameter x, and we have a likelihood over data points ys here, conditionally on x. Then we can define the teeth target distribution as the posterior, where we include the first t data points. This would correspond to some kind of data tempering. Or we can consider another situation when we take the teeth target distribution to be the prior times the full likelihood of all the data raised to some power tau t, where this tau t is a tempering sequence gradually increasing from 0 to 1, which means that we gradually move from the prior distribution to the full posterior distribution. This is a bit different from the other examples that I showed you, because here we have a sort of fixed target variable x. So even though we have sequences of target distributions that we want to track, they are not defined on sequences of spaces of increasing dimension, which I said was a basic condition for SMC. But it turns out that we can introduce this or increase the space of the or the dimension of the space on which these distributions are defined by introducing auxiliary variables. And one generic way of doing this is to introduce a so-called backward Markov kernel. And we then define the target distribution pi t, which is now a distribution over x1 to t, by saying that, well, the last variable here, xt, that should marginally follow pi tilde t. And then we regenerate all the previous variables by just sampling from this backward Markov kernel down to time 1 or iteration 1. And we then view all of these additional variables as auxiliary variables, and we can then target this sequence using SMC. And importantly here, by construction, this target distribution pi t will admit the pi tilde as a marginal. So if we can track the pi t distributions, then we also get samples from pi tilde. Right, so those were a few examples of application domains or like example problems where we can use SMC and where SMC has been used, which goes beyond the dynamical systems setting. So turning now to what the algorithm actually does. As I said before, SMC is an iterative application of importance sampling for tracking this sequence of target distributions. And this means that at any iteration of the algorithm, we will have one of these empirical point mass distributions or weighted point mass approximations, pi hat approximating the current target distribution. And this will then consist of a set of capital N samples, x1 to ti, and corresponding importance weights, wi. So to see how we can generate these approximations sequentially, assume that we have such an approximation available at time t-1, and we'll now see how we can transfer that to an approximation at time t. And at the initial time point, we'll of course just initialize using standard importance sampling. So the first thing to do here is to simply note that we can write the target distribution at the current iteration pi t by simply multiplying and dividing by pi t-1 in this way. And based on this expression, we can now plug in our approximation of pi t-1. So we get pi hat t-1 here. And this will then give us an approximation of the target distribution at the current iteration. Now this approximate target is in fact supported on this product space here. It's a mix of a discrete and a continuous space typically, because our pi hat here, this will be supported on this discrete set of points. And then we extend this, you could say, with this, the variable xt, which lives in this space, curly xt. So we have a target distribution supported on this product space. And since this collection of point masses here, that's a discrete finite set, we can identify that with the set of integers 1 to n. So we can equivalently say that this is a distribution over this product space, the discrete set 1 to n times the curly xt. So based on this view, one iteration of SMC is simply applying self-normalized importance sampling to this target distribution using some proposal distribution defined on the same product set. And in particular, I will denote this proposal distribution by these two quantities here, the nu and the q. Nu, that is a proposal for the discrete variable living in this set 1 to n. And the random variable that lives in this, the discrete random variable, I will denote by AT, and it's commonly referred to as an ancestor index. And we then introduce a proposal for this ancestor index, which is given by the nu variables, and nu is simply a probability vector over the integers 1 to n. And then we have another part of the proposal, which is then a proposal distribution for the variable xt, and I denote that by q. And this is conditionally on the value of a, or equivalently then, since we can identify each value of a, each integer here with one of the previous samples, I can condition this on a sample x1 to t-1. And using this proposal to sample from this target star here will then allow us to move from an approximation of pi t-1 to an approximation of pi t, and then we can continue from there. Okay, writing the same thing more in terms of an algorithm or pseudocode-like, it looks like this. So one iteration of SMC can be seen as consisting of 3 steps. The first 2 steps just correspond to sampling from the proposal distribution. So first we sample the A variables, the ancestor indices, and they are discrete random variables on the set 1 to n. And we have our proposal distribution, the probabilities nu here. So we sample n such variables independently from this categorical distribution. Conditionally on these variables, we sample from the proposal over x. So we sample xt from the proposal q, conditionally on its ancestor. We can then construct new sort of particle trajectories by appending the newly sampled xt here to the history on which it is conditioned. And then in the third step, we simply compute importance weights for these newly sampled particles. And this expression here might look a bit messy, but it's simply the ratio of the target over the proposal when the target distribution is given by this expression here, up to normalization, and the proposal is given by this product down here. So a standard importance ratio. And carrying out these 3 steps will then obtain a new set of weighted particles, weighted samples that can be used to approximate pi t. And then we can continue with the next iteration of the algorithm. Okay, so looking at this, we see that there are a few design choices that we need to consider. And oh, sorry, I forgot to mention this, that similarly to the standard importance sampling algorithm, we get an unbiased estimate of the normalizing constant from this procedure. And we get that simply by taking the product over all of these averages of the unnormalized importance weights. So that property carries over from standard importance sampling, which is a nice byproduct then of SMC as well. Right, so I was saying there are a few design choices, and the most obvious one is probably the proposal for the x variable, and this is one of the design choices that has received most attention throughout the years. And as you know from, or similar to standard importance sampling, it's important to pick a good proposal distribution here. It turns out that we can compute what the locally optimal proposal distribution is, and locally here refers to the fact that it's optimal for approximating pi t, but not sort of looking ahead at what will happen at the next iteration. But if we only sort of focus on approximating the current target distribution at iteration t, then the locally optimal choice is a proposal distribution that is proportional to the ratio of the unnormalized targets gamma t and gamma t minus 1. This can, in some cases, be evaluated exactly, or in other cases, we can at least use this as a guidance for approximating this ratio and using the approximation as a hopefully efficient proposal distribution. Another design choice here is the proposal distribution for the A variables, the ancestor indices. Similarly to Q, we have an expression here for the locally optimal choice, and it turns out that the optimal thing to do is to select these probabilities nu simply by according to the normalizing constant of the optimal Q. Now, this is something which is well known in the literature, but I think in my experience, it's not used as much in practice as sort of constructing a good approximation to the optimal Q. And this is a bit of a pity because you can see from these expressions that they're highly related. And typically, whenever you can compute a good approximation of Q, you also get the good approximation of the new proposal as a byproduct. So I think that is something that could be used more. The most common choice is, of course, just to select the new new variables according to the previous importance weights, WT minus 1, which means that this first term here in the weight function cancels. But there's really not necessarily a good reason for doing that. It simply corresponds to sampling the A variables from their prior, you could say. Right. So as I mentioned before, in a lot of applications, we are in fact only interested in the final target distribution pi n, and the intermediate targets are just a means of getting there. And this has at least 2 interesting implications. And the first implication is that it means that we can actually optimize the proposal distributions not locally at each iteration, as I mentioned before, but viewing this more as a global optimization, in that we would like to find a sequence of proposals QT for all iteration indices here from 1 up to n, and find this by some global or offline optimization such that we get an as good approximation of the final target as possible. And this can very well result in proposal distributions that are different from these so-called locally optimal. Another implication is, as I mentioned before, that we can also view the intermediate targets, so the gammas, as design variables that can be optimized. And the intermediate targets, that would be all the gammas from t is equal to 1 up to n minus 1. And the final target, gamma n, will of course be fixed because it corresponds to the original target distribution of interest that we want to sample from. I will just say a few words about the first point here, A, before turning to the second point, where I will spend a bit more time in the talk. But yeah, a few words about the first implication, how to optimize the proposal distribution. So as I mentioned, we can think of this as solving some kind of global or offline optimization problem. And one way of doing this is to mix SMC with variational inference. And again, here we have at least two different options for how we can do this. And the first option would be to say that, well, we're interested in this pi n. So if we can construct a variational approximation of this pi n, which I denote by qn here, and this variational approximation factorizes into a product of q distributions, of conditional distributions in this way, then we can use qt as the proposal distribution at iteration t of an SMC algorithm. And we can also then use the SMC algorithm for computing stochastic gradient for the variational inference method. So we can then, in some sense, entangle these two approximate inference methods. The SMC is used to compute the gradients for the variational inference, which is then used as the proposal for the SMC. And I actually have one more slide on this, so I'll get back to that. But I also just want to mention a second option here for how we can merge variational inference and SMC. And that is to use the SMC approximation itself as a variational distribution. And what I mean by this is that we view or define our variational approximation simply by an implicit procedure where we run the SMC algorithm, and at the final iteration, we pull out one sample from our SMC approximation. And then we define that to be one sample from the variation distribution Q. So formally, this means that Q is defined to be the expected value of this empirical measure pi hat n. And this can then again be optimized using more or less standard variational inference. And this is the second approach here, is what's referred to as variational sequential Monte Carlo. But yes, I mentioned I have one more slide on the first option here, which is based on using a parametric variational approximation of pi. And we then want to optimize this by minimizing some distance between q and pi, as in standard variational inference. One thing that we need to consider, though, when doing this is that we want to use q in some sense as a proposal distribution for an importance sampler or an SMC algorithm. And if we do this by standard Kullback-Leibler minimization, by minimizing the so-called exclusive Kullback-Leibler that you usually use in variational inference, then there's a tendency of underestimating the variance of pi, and using that together with importance sampling, we can typically end up with very high variance approximations in the importance sampler. So to mitigate this issue, what has been proposed instead is to flip the order of the Kullback-Leibler minimization around. So we instead look at the inclusive Kullback-Leibler divergence between q and pi, which can then be written as simply this cross-entropy term plus some constant. So we want to minimize this cross-entropy with respect to the variational parameters lambda, which will also serve as proposal distributions then in the SMC algorithm. The difficulty of looking at the inclusive Kullback-Leibler is, of course, that the expected value here is with respect to pi, the target distribution of interest that we're computing this expected value explicitly is not feasible. Then we wouldn't need this procedure in the first place. But what we can do is to still try to optimize this objective using stochastic gradients. And one way of doing this that we have explored recently, which we refer to, or in a method which we refer to as Markovian score climbing, is to use this variational approximation within the SMC algorithm, as we said, as a proposal. The SMC algorithm is then combined with an MCMC routine for computing approximate gradients of this inclusive Kullback-Leibler term. And based on a Markovian stochastic approximation argument, we can then show that this, under some admittedly rather strong conditions, but still under some conditions, it converges to a local minimizer of the inclusive Kullback-Leibler. I can also mention that this Markovian score climbing algorithm is not restricted to SMC. It's sort of a rather general method for optimizing the inclusive Kullback-Leibler within variational inference, but it can also be used together with SMC, and we have examples of that in the paper as well. Okay, so that was one of the implications that I said of looking at SMC as an offline problem, that we can globally optimize the proposal distributions some way. The other implication was that we can also optimize the intermediate target distributions. And that is what I will turn to next in the second part of the talk then. And we will do this by looking specifically at an application example, inference in graphical models. So if you recall what I said before, in a factor graph, which you can use to represent both directed and undirected graphical models, we have a joint distribution which is given by a product over some factor set, where each factor here depends on a subset of the variables x1 to n. In sort of the standard, if we can call it that, the standard SMC approximation or SMC approach to sampling from this joint distribution over the factor graph, we define the intermediate targets using this idea of a sequential graph decomposition. So gamma t is given by the product of all the factors involving only variables x1 up to xt. So to show you what that means a bit more, I have a small illustration here for this, small factor graph. Just to give you an idea of what it looks like. And in the first iteration, what we'll do is that we introduce the first variable x1, and that means that we just take the first factor f1, which is the only factor that only depends on x1 here, and our target or intermediate target distribution will then simply correspond to this small subgraph. In the second iteration, we introduce the variable x2, which then also means that we can include factor f3 here, and we get the target distribution corresponding to the product of those two factors. And then finally, at the third iteration, we include the variable x3, and that means that we can now include all factors of the model in our target distribution, and then by construction, we get an unnormalized target distribution, which is proportional to the full distribution over the graph. And as I said, we can use this, and we can apply an SMC algorithm to sample from these distributions, and it will be a consistent algorithm. We will get unbiased estimates of the normalizing constant and so on. But in practice, the fact that we are simply neglecting the intermediate or simply neglecting the factors that depend on some kind of future variables at the intermediate steps can degrade the performance of this algorithm. So to try to mitigate this, we can use the fact that all the intermediate targets are design choices, and we can try to use that flexibility into constructing a better sequence of intermediate targets. And the way we'll think about this is that we will use the so-called twisted target distributions instead. And the twisted target here referred or denoted by gamma psi, but it's simply taking the original unnormalized intermediate target at the iteration t, or gamma t, and multiplying this with some non-negative function, a so-called twisting potential, which I denote by psi. And intuitively, the role of these twisting potentials is to serve as a type of look ahead for the algorithm. So at the initial time point, we still take the first factor and the first variable and include them in our model. But then we have the psi function, which tries to look ahead at all the things that we have excluded from the model and correct for those dependencies. At the second iteration, we again include x2 and we include the factor f3, and then we have a twisting potential at this iteration, looking ahead at the things neglected at this iteration, and so on and so forth. And again, importantly, when we reach the final iteration, we have included all the factors of the model, and we recover a target distribution which is proportional to the original target of interest. Put differently, at the final iteration, the twisting potential will always be equal to 1, so that we, at the end, sample from the correct distribution. Okay, the obvious question is, of course, how do we select these twisting potentials in some good way? And to answer that question, we can first ask ourselves, okay, what would the optimal choice of twisting potential be? And it's quite easy to show that if we select these twisting potentials according to this way, so we get an integral over the future variables of the model, you could say, then the SMC algorithm that we obtain will actually output IID draws from the full target pi, and the normalizing constant estimate of this SMC algorithm will actually be exact with probability 1. So this would mean that we have, in some sense, the optimal choice of twisting potentials. The draw, or the issue is, of course, that computing these optimal twisting potentials is just as difficult as computing pi in the first place. And there's, as always, no free lunch. But what makes this interesting still is that we can approximate these twisting potential, the optimal twisting potential psi star. And we can do that essentially by any deterministic inference method that can be applied to a probabilistic graphical model. And importantly, in doing so, the suboptimality of that deterministic approximation, it will only affect the efficiency of the SMC algorithm, not the consistency or not the unbiasedness of the normalizing constant estimate and so on. So we can view this combination then as a type of bias post-correction of the deterministic inference method that is used to approximate the twisting potential. So I have a few examples of how this can be done. So one such deterministic method that we might consider using is expectation propagation, in which case we approximate the distribution over the graph by introducing approximate factors, fj, and these factors are updated iteratively by a Kullback-Leibler minimization objective. Based on these approximate factors fj, well, we get a natural approximation, simply plugging those approximations into the integral and computing psi in this way. So to test this ID, we apply that to an example in topic modeling. So we look at computing the held out likelihood in a latent Dirichlet allocation model. And we then use the special purpose EP algorithm for approximating the twisting functions. And here we have some results in these figures. Maybe the medline plot here is the most interesting one. That's a real data set. Here we have a small toy example, but in the medline we have some real data where we look at the estimated log normalizing constant, log marginal likelihood. And without going into too many details, we can say that higher is better here. And what we see in this figure is first the dotted line corresponding to the EP approximation. Then we have the red box plots. These are estimates obtained by a standard SMC algorithm without the twisting for different number of particles. And then we have the bluish box plots corresponding to the twisted SMC algorithm. And what I think is interesting with these results is that using this idea of twisting SMC based on an EP approximation, we can actually outperform quite significantly both of these baselines, so both the EP algorithm and the non-twisted SMC. Okay, I have another example here with a Laplace approximation that we can use for latent Gaussian Markov random field models, and use Laplace approximation to approximate the twisting functions. I think that I'll actually skip this in the interest of saving some time and jump directly to just a quick summary and outlook. So to summarize, I've presented sequential Monte Carlo as a generic tool for approximate Bayesian inference. And in particular, I said that we can use SMC to approximate essentially any sequence of distributions, which is defined on a sequence of spaces of increasing dimension. One iteration of SMC simply corresponds to self-normalized importance sampling for the current target, but where we use the previous approximation to approximate the target. There are some key design choices in SMC, including the resampling weights, the new variables, as I refer to. We have the proposal for the X variable, and in particular, then what I think is worth highlighting here is that for these offline problems where we only care about the final target, we also have the intermediate target distributions as design variables. And this leaves room for some flexibility and for being a bit innovative in how we can select these target distributions to obtain a good performance in the end. And one way of thinking about this is in terms of twisting, which simply means that we start with some natural sequence of target distributions, and then we add a multiplicative twisting potential that can then be optimized in some way. Naturally, there are a lot of things that I haven't covered in this talk about SMC. Just to mention a few of these things, while I haven't said anything about the convergence, there's by now a fairly substantial amount of convergence theory related to consistence, stability, path degeneracy, and so on. And then more on the method side, there's a lot of work on combining SMC with other approximate inference methods that I find interesting. I touched a little bit upon using SMC together with variational inference, but there's much more that can be said about this. There are also algorithms for using SMC within SMC, for instance, for solving high-dimensional problems, doing distributed SMC, online parameter learning, and so on. And the final combination here is to use SMC within MCMC to construct high-dimensional MCMC kernels, you could say. And this leads to something which goes under the umbrella term of particle Markov chain Monte Carlo. So there are different ways of doing this, resulting in efficient MCMC kernels based on SMC. But yeah, as a final advertisement, then you can read about all of this in our tutorial Foundations and Trends paper elements of Sequential Monte Carlo. And with that, I'm happy to take any questions.
Okay, thank you, Fredrik, for the great talk. So yeah, we do have a few questions in the line. So the first question is for the first part of your talk, are there any extensions to distributed SMCs?
Yeah, there are. I mentioned one approach here on distributed SMC where you connect multiple SMC algorithms that are on different computing nodes, you could say, and then the way in which they interact is through another level of SMC. So you have multiple SMC algorithms running locally. They communicate their normalizing constant estimates to some central node, which then is responsible for like a top level SMC implementation, you could say. So that's one approach, and there are other approaches as well. You can also distribute more on the granularity of different samples or particles, so that each compute node is responsible for essentially one particle.
Okay, so another question is for the second part of your talk, are there any bootstrapping bounds that needs to be followed for the optimal approximations?
If there are any, what type of bounds you said?
Bootstrapping bounds.
for, is this referring to the twisting potentials here?
Yeah, I think so.
I'm not sure exactly what it refers to, but no, this holds quite generally as long as all the intermediate targets are normalizable. They should be integrable. Then you will have this this property. So.
Okay, I'm not exactly sure if that answers the question, but
I'm
yeah.
not sure either if I understood the questions. Maybe you can elaborate a bit.
Bootstrapping or startup values?
Startup values, but it's not an iterative process. So no, I mean these are computed, you could say, offline as a pre-processing step, and then we use these. Still not sure if I understand the question.
So you are saying that you need to first compute this sort of like, say, optimal twisting offline before you actually run the SMC procedure.
Well, the way in which we do it in this, the second part, that's the approach that we have taken, yes, that we use EP, for instance, to approximate the twisting potentials, and that's done in a pre-processing step, and then you run SMC based on those. But also this proposition that applies to the actual optimal twisting function, so it's not based on any approximation, just saying if we compute them in this way, then we have an SMC algorithm that is in some sense exact.
Okay, I think the person who asked this question said that this answered his question. So yeah, I have a related question. So you mentioned that you use this massive passing or EP approach to compute these approximated twisting distributions. I was wondering, when the graph has many loops, and we know that EP might not converge or might converge to some different answers when you run differently. So how would you comment on these stability issues? How would that impact on this SMC procedure?
Yeah, it's a good question. I mean, we don't have any optimality guarantees when using a deterministic approximation. So, and I don't really have much more to say about that. It's kind of, we run it and hope for the best. Still, the way I like to see it is that we are doing some kind of, as I said before, biased post-correction of the EP algorithm. So more or less, regardless of how we select the twisting potentials, we have a consistent Monte Carlo algorithm. And also you can then use convergence diagnostics for SMC to maybe actually figure out that the EP approximation is probably no good because the SMC algorithm is not performing as well as it should. We know that if we are very close to the optimal twisting potentials here, then we will get a very high effective sample size in the SMC. Ideally, it will be a constant effective sample size of n at all iterations. If there's a significant drop at some point, that is an indication that the SMC algorithm is, or that the twisting potentials are clearly suboptimal.
Okay, so maybe a last question. So in this talk, so you mentioned that we can either, say, optimize the proposal distributions, or we can design these kinds of intermediate target, right? So maybe can you comment a little bit about like the comparison between the two? So for example, say in which cases you might prefer to do, say, designing this intermediate distribution, or in some other cases, doing the other thing would be easier.
I think usually we do both, or at least when we optimize the twisting potentials, we also get the proposal distributions as a byproduct, more or less. So in this paper, we look at graphical models and how we can use deterministic approximations for approximating these size. We also get the good approximation of Q, like a good choice of Q, you could say. And then the question is it necessary to optimize both, or is it enough to optimize the proposals? And I think looking, for instance, at these variational SMC algorithms that have been proposed that focus only on optimizing Q, but you optimize it in order to get a good approximation in the end at the final iteration. That seems to work pretty well, even if you don't optimize the intermediate targets. So in some sense, it seems like you can find a good set of proposal distributions Q to compensate for a suboptimal choice of the gammas. But I don't think that has been formalized in any way. And I think intuitively it would make sense to optimize both, but I think a lot of ongoing research there still on what is the best approach.
Okay, great. So I think this concludes the first session about the evaluation lecture. So definitely thanks, Fredrik, for this great lecture. So for the next one, we will go for the contributed talks. So I will share my screen. Okay, so the first talk will be bijective contrastive estimation.
Hi, my name is Jaehyun Lim. This is a joint work with Chinwei, Aaron, and Chris from Mila. I'm going to introduce a new classification-based training method for unnormalized density models called bijective contrastive estimation. One way to characterize a random variable is to describe its density. Energy-based models define a density functions by exponential of negative potential functions and the corresponding normalizing constant. One important property of EVM is that its parameterization has almost no constraint, and therefore it's easier to parameterize a flexible density function. However, it's difficult to maximize the likelihood of EVM for training. It's because the estimation of log partition function is usually intractable, and generating samples from the energy function is not easy, even when computing a gradient. In order to avoid these issues of MLE, other training criteria has been proposed. For example, noise contrastive estimation, score matching families, and many others. In our attempt to devise new training criterion, we introduce a new classification-based method to learn EVMs from data. Then how to learn a normalized density by classification. Suppose we have samples from two distributions, a data distribution P data and a contrasting distribution Q. We randomly sample a data point from either one of them with equal probability, resulting in the blue curve in the figure. And our task is to determine which one is the source distribution of the observation. For this classification problem, the optimal probabilistic classifier is the posterior distribution of the source given the observation. When you have knowledge of the contrasting distribution of Q, you can plug in the above classifier. And then you can define a classifier that depends only on a model that approximates P data. The learned model in the classifier will recover the data density. This is called noise contrastive estimation, typically when one uses energy-based model in approximating P data. In this work, we define a contrasting distribution in a different way. To create a contrasting distribution, we transform the data using a bijection or invertible function. Again, let's consider a classification problem. Here we produce a contrasting distribution by applying an invertible transformation to data. By using the change of variable formula, we write the density of the transformed random variable as a product of a probability of preimage of x on the source distribution and the Jacobian determinant of the inverse transformation evaluated at x. For this classification problem, the optimal probabilistic classifier is the posterior distribution as in the previous example, but with the density we described in the above. By plugging an energy model in place of P data of x as a P data of preimage of x in the classifier, we define pi. This classifier pi naturally cancels out the normalizing constant. We then learn the energy model to recover the data density by training the classifier. For example, we can consider addition as bijection. The black line describes a data density and the red line correspond to the contrasting distribution, in which we shift the original data by amount of epsilon. The probability of the data point being sampled from the original data is described as blue. Here, one may notice that we can learn the data density by using this one optimal classifier. This is because different density can produce very similar optimal classifiers. Let's see the figure in the top row. The top left is the same example in the previous slide, and the right side depicts another density and its contrasting distribution generated with the same bijection. The optimal classifier on the right side is very similar. Therefore, without knowing any further information about the data, we won't be able to recover the data density from the classifier. On the other hand, the family of optimal classifiers generated by a large collection of bijection will be uniquely dependent on the data's density function. Here, we have the same density as above, but we use multiple bijections to generate multiple contrasting distribution. The behavior of two different sets of optimal classifiers are distinguishable. In other words, with an increasing number of classification problems, there will be less available density that match all of the optimal classifiers of the generated problems. This means we can use the same energy function to solve more classification problems, and this will hopefully rule out all but one density function, which is the data density. As a result, we learn the density by parameterizing all classifier as a function of one energy and all bijections. We then jointly solve the class our method bijective contrastive estimation. Then is any bijection okay here? One of the simplest failure case you can imagine is when bijection T is an identity function. We show that under some mild assumption on the distribution of bijections, the unnormalized density of the minimizer of BC loss must be proportional to the data distribution. The intuition of the condition in the theorem is that as long as the bijections distribution allows to compare enough number of points, then the functional solution of learned unnormalized density will be proportional to the data density. One of the simplest examples is additive transformation following a Gaussian distribution. We show that the additive bijections satisfy the condition of the theorem. Operationally, we can simply sample noise from a Gaussian and add it to data, and then train the classifier using the corresponding loss function. As an example, we run density estimation experiment on 6 2D synthetic data set by minimizing the PC loss with the additive bijections. The top row in the figure shows the density of the synthetic data set we want to approximate. And the bottom is the plots of the energy function learned by BCE. The result demonstrates that the energy trained with BCE accurately model the 2D synthetic data. Interestingly, when the distribution of bijections and the distribution of their inverses are the same, we can simplify the computation of BC loss. In the original loss on the top, the first term and the second term are equivalent in expectation, and so the loss reduces the next line. For example, consider the additive bijections with zero mean normal distribution. Their inverses also follow the same normal distribution. And instead of generating binary classification problem, we can extend BC to generate multi-class classification problem. Instead of generating one contrasting distribution at a time, we apply multiple bijections to data. We then learn to classify multi-class classifiers parameterized similarly to the binary case. If the distribution of bijection and their inverses are the same, then we can also reduce the multi-class loss into a stochastically averaged version. In the preliminary experiment, we observed that the multi-class BC loss makes the training faster. In other preliminary experiment, we observed that the proposed method did not work well on high-dimensional data, such as image data. We observed that the loss does not provide meaningful learning signals when a generated classification problem is too easy to solve or a contrasting distribution is too close to the data manifold. For instance, for additive bijection in the image data, the classifiers achieve near perfect accuracy while the learned energy is nowhere near to the true density. We're guessing that this happens when the transform random variable is far from the current energy model. On the other hand, the gradient with respect to their energy can also vanish when t is near identity. In this case, regardless of the shape of the energy, the gradient with respect to the parameter are approximately zero. We aim to address this issue of BC loss in the future. In this paper, we propose bijective contrastive estimation. We prove that the data density up to normalizing constant is the only minimizer of the BC loss in non-parametric limit. In the experiment, we show that the energy trained with BCE accurately models the 2D synthetic data. We also discussed the difficulty of BCE training in modeling high-dimensional data. Thank you for attending this talk, and I'd like to thank this amazing collaborator. Thanks.
Okay, so thanks for the great talk. So now the author Hyun Lin is online. So Hyun, you are muted.
Hi.
Okay. So you can submit your questions through the Q&A part. So maybe I can start from one question. So you mentioned that your method has some problems working on high dimensions. Are you referring to the additive Gaussian noise version, and why is that?
Yes, I think it's not only the Gaussian noise case. I think even with the structured noise, we're experiencing like a losing learning signal. I think we consider it's very similar to the failure case of the noise contrastive estimation in a way that so in the submitted paper, we thought it's the unstructured, adding the unstructured noise just easy to classify by the classifier. But we don't have a clear conclusion why that might be the case. But I think we start have some clue. Yeah. But I think the relative discussion have been submitted in the iClear. So it's actually, yeah, I think that's my current answer.
Okay, great. So we have another question coming in. So for the empirical evaluation for the 6 2D data sets, how were the quality of the samples evaluated? So essentially, how do you compute the quantitative metrics for your 2D samples?
We didn't have any. We didn't have any quantitative evaluation of the quality of the sample because Yeah, because like for many class of generative model, it's quite difficult. It's quite easy to evaluate the quality by visual inspection. So I think it's a good indicator that the method works in the low dimensional data. Yeah.
Okay, so the other question, maybe you have already answered partly, but I think this is again asking how does the observation that your method fails in high dimensions compared to like the failure in at the standard noise contrastive estimation?
Mm-hmm.
The hypothesis here is the standard noise contrastive estimation has the issue because you need a contrastive distribution to overlap somehow with the data density in order to make it work well.
Yes, probably, but I think our understanding of the problem is a little bit different. But so genuinely, I think the audience preferring the contrastive flow contrastive estimation, which like adversarially training the generator in the noise contrastive estimation. That is correct, but I think the recent discussion is that our summary clear mentioned that the distribution actually need to be closer to the current energy rather than the data distribution. So I think that's actually good analysis. Yeah. So in conclusion, our understanding is the current distribution is supposed to be closer to the energy rather than the data. So I think that's like determine the learning signal. Yeah. Does this answer the question, I guess?
Maybe a bit. Maybe this is still an open question that needs research. So
Okay.
yeah. So let's thank Jackman again, and we will go to the second contributor talk. So let me share my screen. So the second talk will be evidence estimation by Kullback-Leibler integration for flow-based variation inference.
Welcome to this talk about our paper at this year's AABI symposium. Our paper presents a new method of computing the evidence in Bayesian inference with certain variational inference algorithms. In this talk, I'm first going to go over the definitions and background. Then I'm going to talk about which variational inference algorithms can be used for this and how it can be done. And then I'm going to show how it is actually done on a specific algorithm. This is, of course, Bayes' theorem, where the target distribution or posterior distribution is the thing that we're trying to approximate or trying to find ideally. And the problem is often that we cannot compute the normalization constant, which we denote z and call the evidence. One way to do Bayesian inference has been quite successful is variational inference, where we try to approximate the posterior distribution by something called a variational distribution Q. And this is typically done by considering a range of distributions and then choosing the one that minimizes the Kullback-Leibler divergence is given here. Now often these families are parametric families, so that can be quite restrictive, but it's much easier to solve. However, recently there have also been more non-parametric approaches, and these are what we focus on here. In particular, a class of approaches that we describe as flow-based variational inference, and they can be characterized in the following way. We start with an initial random variable that is some distribution that is easy to calculate or is our best guess, and then we transform that random variable according to this ODE flow. Now in practice we have to discretize the time, So what usually ends up happening is that we just update the random variable at each step with some small perturbation. Now hopefully this will then converge to the target distribution. Now in this context we have to of course consider what happens to the KL divergence, and this can be expressed in the derivative of the KL divergence, which is given here. Now this is the basis for the example that we'll be using, namely Stein variational gradient descent, or SVGD for short. SVGD starts by considering this derivative of the KL divergence and then asks what is the optimal phi in this case. What generates the largest negative value for this derivative. And it turns out that an analytical expression can indeed be found under the relatively mild condition that phi lies in the unit ball of a reproducing kernel Hilbert space. The connection between this is the so-called Stein discrepancy, or to be more specific, the kernelized Stein discrepancy, which is defined as follows. It is the maximum of the expected value that we saw in the derivative of the KL, taken over all test functions phi that lie in the unit ball of a reproducing kernel Hilbert space. Now, just to recall some detail, this is what it means for phi to lie in a reproducing kernel Hilbert space. So there's a linear combination of a single positive definite kernel. The optimal phi is then given by this. And now we basically have everything that we need to build an algorithm out of this. Everything left to do is replace the random variable with an empirical distribution and to replace all the expected values with averages. To summarize then, this is the algorithm that we get. This is the Stein variational gradient descent algorithm. What this basically does is take some particles and then moves them around until they represent samples from the target distribution. So we have a little animation, hopefully it will work, to illustrate this for those that haven't seen it before. Essentially at each iteration the particles are attracted towards the target distribution and repulsed from one another so that they spread out appropriately. Now, of course, the question is, how do we get the evidence from this? And for that, suppose we have such an algorithm as described above, some flow variational inference algorithm, and we write the target distribution in this exponential form, where we call v of x the potential. And the central result of our paper is that the log of z, the log evidence, is greater or equal to the entropy of the initial distribution, which we denote here by h of q0, minus the expected value of the potential under the initial distribution, minus the integral of the derivative of the KL divergence. And indeed, the proof is quite simple, and it illustrates why it's an inequality and in which circumstances equality can be obtained. So there are really just two parts. One is the definition of the KL divergence of Q0 with the target, and this can be expressed here as the sum. And the other one is the fundamental theorem of calculus, which tells us that if we integrate the derivative of something between a and b, it will be that something at a at b minus that something at a. Now Q0 here denotes the final distribution of our algorithm. Of course, it's not infinite time, but once the algorithm has converged, everything after the time should be negligible. So using this, we just do flow vi as usual, updating the random variable at each step. And at each step, then we also compute the derivative of the KL divergence. Note here, by the way, that the derivative of the KL depends only on the flow and the gradient of the log of the posterior. Now these are things that we already know, and they're not hard to know. And then we can just approximate the log evidence by substituting a sum of the derivative of the KL values that we have for the integral above. Now, if we look at what this does to SVDD, it essentially adds one extra step, which each iteration we also have to calculate the derivative of the KL. This is indeed not as trivial as it sounds here, because we have to estimate this as well. And we found 3 ways to do this in SVGD. One, the most obvious one, is of course to use the kernelized Stein discrepancy, because the derivation of SVG started by asserting that the derivative of the KL was equal to the negative of the kernelized Stein discrepancy if phi is chosen optimally. In the paper where the kernelized Stein discrepancy was first introduced, 2 estimators are also presented. The most straightforward one of just numerically calculating this expected value as an average has the nice property that it's non-negative. Unfortunately, it's a biased estimator, but it can easily be converted into an unbiased one. So we'll be referring to these as the Stein discrepancy and the unbiased Stein discrepancy. Fortunately, neither of these worked very well in our experiments. And so we had to look for a new one, which we found in the RKHS norm. And for this, I have to introduce a new result, which is that for the optimal phi of t, it holds that the Stein discrepancy is equal to the RKHS norm squared of that phi. Now, this can be estimated, as you can see here. The details are not so important. If you want them, you can pause the video, and I think it should all be there. The important part is that this is a function of phi of t evaluated at the particles. So if our algorithm converged, then the particles would not be moving anymore, and therefore phi of t should be 0 there everywhere. And this is a nice property, because if there's a small remainder, then running too many iterations will skew the result. This is the problem that we had when using the Stein discrepancy. Now for some quick examples. We tested this on what is probably the simplest of all cases, namely choosing an initial distribution that was standard normal and a target distribution that was also normal. For the kernel, we used a typical radial basis function kernel. And here you can see the results for 3 step sizes and also for the 3 different estimators. Now, on these plots, unfortunately, all the values, they start so negative that it's not easy to see the difference between the Stein discrepancy estimator and the RKHS norm estimator. However, if you look closely, or if you run this multiple times, you'll see that the Stein discrepancy estimator tends to overestimate more than the RKHS norm estimator, whereas the unbiased Stein discrepancy unfortunately often turns negative. We've also tried this with different targets. We can see that this heavily affects the speed of convergence. So if the target is only different in variance, of course it converges very quickly. If it's only different in mean, as on the right hand side, then it converges somewhat slower, and if it's different in both mean and variance, then it converges even slower. I think the most interesting plot is on the next slide, though, where here we're comparing the effect of running this with different numbers of particles. The SVGD scales very poorly with the number of particles, but this result scales well with it, let's say. So the more particles we have, the less we overestimate it. So thank you for listening. Just to summarize, flow-based variational inference is quite a broad class of variational inference, and flow integration, as we've presented here, should be applicable to any such algorithm. It also doesn't require much. It only requires the joint distribution and the gradient of the log thereof. And it has the very nice property that the better the variational inference is, the better the estimate will be. Thank you again, and goodbye.
Okay, great. So we have Nikolai online with us. So let me check. Okay, so okay, let me go for the second question first. So is there some relationship between this approach, your approach, and the variational thermodynamic integration?
I think there is. I'm not too familiar with thermodynamic integration myself, but I know that this that it is sort of similar, conceptually at least. Not sure if there are theoretical connections though.
Okay. So the next question is, what's the time complexity and the optimal memory footprint that you think it will be when adding some functional approximations via deep neural networks?
Okay, so the time complexity or the complexity of the algorithm is just what it adds to SVDD. It's just n cubed, where n is the number of particles. I'm not sure where you would add function approximations with deep neural networks in this though, because if you're trying to approximate phi, let's say, then you have to train a neural network at each iteration, which will probably take a long time and a lot of memory. So yeah, I'm not sure how the neural networks would come into this.
I guess maybe this is also related, right? So you can, for example, have a very good initial distribution Q0 train using neural network to parameterize it, right? So how would, for example, like how would the initial distribution and like the design of your flow, impact on the convergence time of your approach?
I think, as we've seen in these just simple examples, the better or the closer the initial distribution is to the target distribution, the quicker it converges. But that is in general something that we want to look at some more.
Okay, so I have a few questions. So from your theory, how would you advise people to design these kind of flow distributions or kind of the flow? Because you say that you can basically just take any flow, right? And then just run it for a very long time, and eventually you can get some good approximation to the loss that.
Well, any flow under which the distribution of the random variable converges to the target distribution, right? So I don't know any specific criteria like that. That's a really good question. Like, what properties of the flow would make this algorithm converge faster? I think there's a paper on particle variational inference from, well, let's see, Liu et al. From 2019. And they present a lot of different methods and also ways of accelerating that. That is something that we're looking at right now. And I think for now, it's still in the stage where this is a very interesting question, and the best thing is to just try as many different flows as we can.
Okay, so from your observation, basically, you said that yes, from the SVGD paper, the gradient of the KL is indeed the KSD, but you said that using the KSD estimation in practice doesn't work well. So can you elaborate a little bit more on why you think this is the case?
So for one, the biased one, I guess it just doesn't work basically because it's biased. And what happens is a lot of the time is that your algorithm kind of gets close to converging, and then there's a sort of constant term left over that you keep adding up at each iteration, and then you overestimate because of that. For the unbiased one, I'm not sure why it's so bad, but I think we discussed. We do have a little piece in that in the appendix of the paper, and it's related to the KSD being dependent also on the gradient of phi, which we can't really assume to be 0.
Okay, great. So yes, thanks for joining us. So I think this is a great talk. So now I will advertise for the next session. So let me share my screen again. Okay, so next week we will have Mi-Jung Park from NPI to present to us a intersection talk between approximate Bayesian computation and also differential privacy. And also we will have another 2 contributed talk, conjugated energy-based models and combining pseudo-point and state-based approximations for some separable guessing processes. So notice that this we have a little bit different time for the next week. So it will be 9 a.m. GMT next Wednesday. So you can also check out the website for the schedule and also the registration link for the Zoom seminar. So thanks everyone for joining us. So we will see you next week.